Hi there, and welcome to episode 3 of True Anomalies, Tales from the History of Science. I'm your host Meg, and now it's time for Lightweight Champs. Everyone knows the sun is pretty heavy, but have you ever thought of weighing light? Well, in 1919, British astronomer Arthur Stanley Eddington set out to do just that, armed with nothing but a telescope, a ruler, and Einstein's prediction that very massive objects like the sun actually bend the space around them, such that light can follow a curved path. The effect is too small to notice in everyday situations on Earth, so Eddington and his contemporaries looked to the stars. The constellations we see in the night sky shift throughout the year because as the Earth revolves around the sun, the geometry changes and we get a different view. Einstein suggested that you could use the shifting stars to test his theory of general relativity. Basically, all you need to do is to determine whether the position of a star seems to change when its light passes close to the sun, and by how much. So you observe a set of stars on a normal night, observe them again with the sun in between, and compare. Since you won't normally be able to see stars near the sun, you've got to wait for a total solar eclipse. Eddington realized that the eclipse coming up in the spring of 1919 would be the perfect opportunity. That's because a very dense cluster of bright stars called the Hyades would line up with the sun at the time of the eclipse, so it would be easier than usual to photograph the stars and keep track of their positions. Sounds easy enough, right? There's just one more wrinkle. Because an eclipse is caused by the shadow of the moon passing over the Earth, the fraction of the sun that appears blocked out depends on where you're standing on the Earth. In fact, for every solar eclipse, there's only a narrow band of locations from which you can see totality. For the 1919 eclipse, this band ended up falling largely over the Atlantic Ocean, so making the right observation required traveling to a remote location first. Eddington convinced the director of the Royal Greenwich Observatory, Frank Watson Dyson, to put together 2 expeditions, one to Sobral, Brazil, and the other, with Eddington himself in charge, to the island of Principe. Dyson's planning was complicated by the fact that World War I didn't even end until 6 months before the eclipse, freeing up the voyage routes at the last possible minute. In Eddington's mind, there were 3 possible outcomes. First, there might be no apparent shift in the positions of the stars. That would mean that the sun's gravity doesn't deflect light at all. The other 2 hypotheses come from deep within the gritty details of relativity theory. There are actually 2 things going on that can deflect the path of starlight. For one thing, photons carry energy, and through the equivalence principle, E = mc squared, that means they also have mass, so they should be affected by the sun's gravity the same way everything else is. If you consider just this effect, then the apparent displacement of a star close to the edge of the sun's disk would be 0.87 arcseconds outward. Eddington called this possible outcome the Newtonian Result because it assumes that the photons behave just like ordinary matter. But there's another effect, and this one provides the true test of general relativity. Einstein predicted that, in addition to the deflection of light caused by the Newtonian effect, there should be a further deflection caused by the curvature of space itself around the sun. So not only does the photon feel the tug of the sun's gravity on its way here, but what it thinks is a straight line actually looks to us like a curved path. If you take both effects into account, you'd expect to measure a displacement of 1.75 arcseconds, about twice the value due to the Newtonian component by itself. By doing the experiment, observing the eclipse and measuring the positions of the stars, Eddington, Dyson, and their teams of astronomers had the opportunity to distinguish between the 3 hypotheses and prove that light had mass. They were weighing light. It took 2 whole months for the expeditions to reach their destinations, but they arrived in plenty of time for the eclipse on May 29th. Eddington, observing from Principe, had bad luck with the weather. Even when the clouds thinned, the skies were only clear enough to distinguish the few brightest stars. The Sobral team, consisting of Charles Davidson and Andrew Cromlin, had better weather, but their main instrument, an astrographic lens, unexpectedly failed, and they had to rely on the backup telescope. Nevertheless, after each team measured their star positions and compared them to the same star field at night, they each came to the same conclusion. The stars were definitely displaced, and the shift was too large to be explained by the Newtonian effect alone. Einstein had to be right. The results were presented at a scientific meeting in London, and the press went wild. Lights all askew in the heavens, Einstein theory triumphs, and hailed as epoch-making were the New York Times headlines, while London's The Times went with the plain and simple revolution in science, new theory of the universe. After that, Eddington lectured extensively on relativity and gravitation, and in 1921, when Einstein came to New York City to speak about his theory, he was greeted with a genuine ticker-tape parade, the only one in the city's history ever thrown in honor of a scientist. Relativity was all the rage, and all it took to prove that it was real was one little test, right? Well, not quite. Actually, there was a lot going on here. For one thing, these measurements required a precision that was at the very limit of what was possible with the equipment of the day. This was no small feat. And let's go back to that astrographic lens that caused the Sobral team so much grief. If you wanted to observe the eclipse for a long period of time, you'd have to keep moving your telescope to keep the sun in your field of view. The astronomers used mirrors, called coelostats, that would rotate smoothly to keep the images on track. After Davidson and Cromlin developed the first 4 plates, they realized immediately that something was terribly, terribly wrong. The star images were streaky and out of focus. Most likely, the coelostat mirrors had expanded unevenly from the sun's heat. But they tried to measure the displacements anyway and came back with 0.93 arcseconds, closer to the Newtonian result than to Einstein's. This result contradicted the data from their backup instrument, a 4-inch lens that had behaved normally. Now they were confronted with a dilemma. Should they discount the plates from the astrographic lens as compromised, or try to reconcile the results? What would you do if you had to decide, not knowing for sure if you'd be throwing out useful data? Looking back, this situation, combined with Eddington's confidence from the beginning that general relativity would be confirmed, might look a little suspicious. Did they just see what they wanted to see and throw out a contradictory result? How much of our preconceived thoughts and theories influence our interpretation of observations? That's something that scientists have to reckon with all the time. On the one hand, nobody works in a vacuum, and it's impossible to collect information without having some framework to help you organize it. But where is the line between having that framework and introducing a bias? Fortunately, in this case, there's enough of a record that we can piece together what actually happened. Eddington did go into the expedition confident that he would prove Einstein right, but he never analyzed the Sobral data. It was Dyson who decided to set aside the results from the astrographic lens, and he was always comfortably skeptical of relativity theory. In fact, when researchers from Greenwich reanalyzed the Sobral plates with modern techniques in 1979, they found a much higher value for the displacement of the stars, and observations of subsequent eclipses continued to uphold Einstein's prediction. So, did one experiment prove general relativity? Maybe not exactly, but those were some pretty valuable observations. You might say worth their weight in starlight.